So I'm here with Andreas Korn on a very rainy, cloudy summer afternoon in the city of Stockholm, Sweden. And Andreas is a stellar astrophysicist at Uppsala University, just up the road in Uppsala, Sweden. He spends most of his time in Stockholm. And we've been talking about a interesting problem in astrophysics, the so-called lithium-7 problem, the lithium problem. What do we mean when we say that, Andreas?
There could be many lithium problems, but the one that we've been talking about is the cosmological lithium-7 problem. And that is the amount of lithium produced shortly after the Big Bang, a few minutes after the Big Bang. That amount is predicted to be 2.7 on a certain logarithmic scale, but it is found to be significantly lower, a factor of 3 lower, in old halo stars, our main tracer of where we can see lithium, and make a comparison with these Big Bang nucleosynthesis calculations as we.
And what do you mean by an old halo star?
These are stars in the outskirts of our own Milky Way. They are metal poor, thus they are very likely quite old, 10, 12 billion years old. So they trace the state of the universe as it was 10 or 12 billion years ago. So they are in principle a good way of learning something about the amount of lithium present in the early universe.
And lithium in the early universe presented itself as what? In two different forms. Tell us.
Yeah, there's two isotopes of lithium, lithium-6 and lithium-7, and in principle there have been two lithium problems, one pertaining to lithium-6, the light isotope of lithium, and then the one to lithium-7. The lithium-6 problem has gone away recently with better spectra and better spectral modeling of these stellar observations that we do with big telescopes and very good high-resolution spectrographs. But the lithium-7 problem is probably still to some level there, even though a significant fraction of it may pertain to stellar physics, the fact that stars destroy some of their lithium as the stars evolve.
And you were telling me that you think you might have a solution, or at least that's what is known as the Speed plateau.
The Speed plateau, yeah.
So tell us what that means.
Yeah.
And also an isotope, basically, before you tell us what the Speed plateau is, just tell us what an isotope is for those who haven't had chemistry in a while.
Right. So there are atoms. Lithium is the third atom of the periodic system. So it has 3 protons, and then in an atomic nucleus you can have a number of neutrons also, and then depending on the number of neutrons you have lighter or heavier versions of that atom. And there is a version that has 6 nuclei, 3 neutrons, 3 protons, that we call lithium-6, and there is a version that has 3 protons and 4 neutrons that we call lithium-7. So we count the nuclei to say lithium-6 or lithium-7.
And the Speed plateau is what?
The Speed plateau is a plateau of lithium abundances found among these old halo stars, where stars of slightly different masses, slightly different ages probably, and also different metal content, how much metal they have show to us in their spectra. They seem to have the same lithium, and that discovery is now some 40 years old, so it's not new. But this was an intriguing and puzzling discovery that was initially interpreted as representing the amount of lithium that they inherited from the Big Bang, the amount of lithium produced in the Big Bang.
And in its isotopic form, lithium at high temperature is very fragile, you said, correct?
Yeah, high temperatures is a relative term here, because actually it's fragile because it is fragile to relatively low temperatures. But relatively low temperatures in the stellar context is a few million degrees. Above 2.5 million degrees, lithium will actually capture protons and disintegrate into helium nuclei. So. And those temperatures are not the temperatures that are reached in the cores of stars, which are tens of millions of Kelvin, but 2 million kelvins you also reach, say, for example, at 70% the radius of the sun. So at the bottom of the convection zone, the temperature is 2 million plus kelvins.
Which means what is a convection zone in our own star?
Yeah, this is the outer layers of a low mass star like the sun, where the conditions are such that mass is moved macroscopically, globally, like in a hot pot of soup, that is convective motion, and so the material that is brought to the bottom of the convection zone reaching temperatures of 2.5 million Kelvin will eventually be depleted of lithium. So
And you were telling me in the interview just now that lithium is not a rare Earth element,
no,
but it is a rare element in the cosmos.
it is a very rare element in the cosmos. It is about 10 orders of magnitude less abundant than hydrogen, and 6 orders of magnitude less abundant than oxygen, which is the most abundant metal, so not hydrogen, helium. Astronomers call all the elements that are heavier than hydrogen and helium metals, which is a little bit odd, but never mind. So it is a very rare element, and that's why we have to look for some particular places to mine it. For example, in Chile or in China.
So it's very important for us, at the moment at least,
Indeed.
for electric vehicles like the Teslas and the other competitors to Tesla who are using it for lithium-ion batteries, also for phone chargers, etc. Correct?
Yeah.
But it's a rare element. And you were telling me something interesting, is that on Earth, lithium is a stable element, and that the batteries that we use for cars or whatever here on Earth are actually the isotopic 7.
Yeah,
element.
that's correct. And lithium is stable because there's no place on Earth that where we reach these temperatures of 2.5 million Kelvin. So, you know, atoms are atoms. You can do whatever you want with them. They will remain atoms. The lithium, when your battery dies in your mobile phone or in your car, the lithium-7 will still be there, and then somebody can take the battery and make a new battery out of it. In principle, that's the main advantage also of this electric revolution that we have.
But in Big Bang nucleosynthesis, at the beginning of the Big Bang, when the first elements were created, lithium represents only a trace element. Is that correct?
Yeah.
And you said that our sun only 99%. It's 99% lithium free. Is that correct? Something like that.
The lithium-7 in the solar system is now in the planets and in the asteroids and the meteorites and so on. In the sun, 99.95% of the lithium is gone because it has been mixed down to layers that are hotter than 2.5 million Kelvin, and there the lithium has disintegrated.
And
so the sun is,
and it's interestingly disintegrated into helium.
That's correct. Yep.
And so the same thing could happen here on Earth if you took raw lithium from a mine and put it in a large hadron type collider.
Yep.
You could bombard it with protons.
Yep.
And it would essentially convert to helium.
Lithium-7 plus proton is 2 helium nuclei. That's the equation. Yep. So that's technically possible in principle. Of course, not on a large scale, but you could do that. But that's the only alchemy that we do on Earth. That type of reactions. But stars do this on a regular basis. They are nuclear reactors.
Back to the issue at hand, this puzzle of why lithium abundances of lithium-7 is so much lower than what we observed in our models of the Big Bang nucleosynthesis when the first elements were created.
Yeah.
Is most of that lithium, I mean, we can explain some of the discrepancy because the lithium has been depleted due to internal mixing and instabilities
in stars.
Yeah. But there's still a puzzle. Right? I mean, you're still puzzled by this.
It's still a puzzle in the sense that we can't quite make the quantitative picture work. I mean, we know that stars deplete lithium. We only have to look to the sun to see that. The sun is not exactly like those halo stars that we use to infer something about Big Bang lithium, but still, they're both low mass type stars. But you know, when we run the most sophisticated models, we can't quite make observations and theory match. And so there is a remaining problem that could point to new physics, and this is what everybody's excited about. It could point to the fact that there is a loophole, a problem with Big Bang nucleosynthesis, even with the very Big Bang theory itself, if you want to push your limits. And you know, new physics is what excites
And what
physicists.
type of new physics would this point to? What do you mean when you say that? People are always throwing that word around.
Well, yeah, that's right. We do. We have other big things to explain. We have dark matter to explain, for example, right? And the standard model doesn't explain dark matter, but we think that there could be, in principle at least, a supersymmetric world of dark matter out there, and maybe the lithium is an indication of that or is it, yeah, of that world, of that dark world of particles. But that's what we built the LHC for in principle, and no signs of dark matter have been found there. Even though we know that physics beyond the standard model exists, neutrino oscillations, totally unrelated to today's topic, are a sign of physics beyond the standard model.
And so if we find that if this discrepancy remains, and you stellar astrophysicists don't find the solution in observations of stars in our own galaxy or nearby galaxies, then we have to go back to the cosmologists who are the people who are making the models or kind of presiding over the big models of Big Bang nucleosynthesis, and say, hey guys, this doesn't work out.
Yeah, that's right. And there's many proposals already now because the problem is now 20 years old, to solve this. But what they have tried to solve is the full problem so far. Now, if we subtract the stellar solution to the problem, the remaining problem is much smaller, which opens up the parameter space of solutions, actually, I believe. So many more types of solutions could be possible because it's a smaller problem to solve. And that is very interesting per se. So I think in the coming years, cosmologists, people working on Big Bang nucleosynthesis will spend time trying to look into this and understand how can we model Big Bang nucleosynthesis without changing the other elements and isotopes. Good agreement, because Big Bang nucleosynthesis is a very successful theory otherwise. It's only that lithium doesn't quite follow that scheme.
And it just seems, it's so ironic to me personally that here is an element, isotope of lithium, the lithium-7, which we, in our current contemporary life, are really so dependent on at the moment, because it's a light element and it provides the necessarily ingredients for these lithium-ion batteries. It's ironic that this lithium abundance is such a conundrum cosmologically, even though this element is so important.
And it's a very special element. When you look to the periodic table, it's the only element that has at least three completely different sources in the universe. One is Big Bang, as we discussed. One is some form of stellar production in the young universe, in what we call population 1 stars.
The first stars in the universe.
The population 1 is the latest stars, to which the sun also belongs.
Oh, the population, right?
Yeah.
Right.
Yeah.
I was thinking population 3, right?
Yeah, population
1. Yeah.
And then there is also we call them spallation processes in the interstellar medium, where just nuclei collide and produce spallation, so break off particles. So out of carbon, you can in principle break out lithium-7 and produce it that way, and also lithium-6. So there's three very different processes that have contributed to the cosmic abundance of lithium, and that is unique in the whole periodic table. It's the only element that is this diverse in its production sites.
And what do we need to be doing that we aren't to solve the problem?
No, I think, as I said, what has to ripen in the minds of the nuclear physicists is that stellar physics plays an important role. We have to be better at quantifying what part of the problem we can predict and solve, and what part remains. Give that information to the nuclear physicists so that they can work with the rest of it. And that is underway, I would say.
Okay, well, thank you so much for your time today, Andreas. We look forward to speaking to you again. Thank you.
Thank you.